So I was thinking about what I should talk about, and I decided I picked this one, which is really you can talk about anything if you have a title like this, I think. But this is actually not my title. I usually title my talks differently, but I went to this SRC event in Abu Dhabi in April, and one of the people who were organizing the event put a title to my talk saying Architectures for Intelligent Machines. And I liked that title, except I thought it was missing something intelligent in the beginning, so I keep using this title now, Intelligent Architectures for Intelligent Machines. This implies kind of that we're building dumb architectures today, and hopefully I'll convince you that that's the case. I believe we're building architectures in a very dumb way, and homogeneity is probably dumber than heterogeneity, sorry about that. So I think we should probably move to a higher plane where architectures are a little bit more intelligent. So let me start with the problem. Basically, we have a huge data problem today with computing. Computing is really bottlenecked by data. And if you're not bottlenecked by data, then your problem is probably not very interesting. And data is really key for many workloads. I picked AI, ML here, genomics. These are probably the fads of the day. I think there's going to be a lot more things that are bottlenecked by data. I think genomics is very interesting for sure. But if you look at these interesting applications, important workloads are all data intensive. They require rapid and efficient processing of very large amounts of data. And the data is increasing. In genomics, for example, I'll give you an example soon. We can generate much more data than we can process in the workloads that we have today. And these are some maybe backward-looking workloads. They're still important. They're fundamental. They're used in many, many substrates, as you can see over here. And they're bottlenecked by data in terms of performance and energy. If you look at small-scale systems like a cell phone, we also use workloads that are very different from the ones that I showed. And they're also bottlenecked by data. And this is an example that I use from genomics. And in genomics, basically, we can sequence more genomes today much faster than we can really analyze. And because we were so successful to develop technologies that have enabled us to reduce the cost of sequencing. You can see this is the cost of sequencing over the years. And this is Moore's law. So we're actually able to sequence genomes much cheaper than Moore's law has allowed us to put devices in a single chip. Anyway, I don't want to go into the details of this, but basically today, if you want to do something with genomes, you have to computationally analyze what the genome looks like. That enables scientific discovery and a lot of medical and health benefits, but we're bottlenecked by data and how fast we can analyze it again over here. And there are devices actually that can produce this data a lot. These are nanopore devices that were introduced in 2014. You can buy these really cheap, $1,000, $2,000. You can do your own genome sequencing of anything you wish, as long as you are able to do that, of course. But you're really bottlenecked by data. People are actually taking these devices and sequencing genomes in Africa, and they're sending the raw data to the data centers in US and Europe. So imagine that we have this beautiful device that can do the sequencing nicely, but we're not able to process the data in that device or close to that device. It's a bit sad, I think. It leads to a huge bottleneck and huge churn that we cause in the entire world. And as a result, we're bottlenecked by data again. I will argue that data overwhelms the modern machines that we build today. It overwhelms the storage and memory capability, communication capability, and computation capability as a result. It greatly impacts robustness, energy, performance, and cost. I'm not going to focus on a lot of these, some of these as much. Robustness I'll briefly talk about, but it's really impacting everything we have. And if you look at a computing system as we know it, this is von Neumann's beautiful paper in 1946. It consists of three components: computation, communication, and storage and memory. And we've heavily optimized the computing unit. Accelerators also are included over here. And we've pretty much ignored what's over here. As a result, the units that we have, this is my cartoonish picture of that, are essentially dedicated to storing and moving data. Most of the real estate that we have on a chip, even if it's an accelerator or a general purpose chip, most of the real estate is dedicated to caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, main memory, other interconnects, and storage. So more than 80 to 90% of the chip is really dedicated for storing and moving data. And we're calling these computing devices. They're not computing. They're really storing and moving data most of the time, as you can see with the amount of real estate we dedicate to it. And this is because I believe we're designing them to be not so intelligent. And as a result, you get these workloads that are performance energy bottlenecked. I'm going to talk about this briefly, but we did this study recently with Google. We've analyzed some key workloads that are used in Google devices. These are 4 key workloads that we analyzed. And if you look at the analysis, you find out that more than 60% of the entire system energy on an Android or Chromebook-like system is spent on solely data movement, moving data in and out of the processor so that you can process it. Okay, we'll get back to this, I think. So I will start with this axiom. I will say that since data is so important, an intelligent architecture has to handle data well. So how to handle data well? Of course, that's the next question. Basically, I think we need to ensure that data does not overwhelm the components. I've been talking about this. How do we get there? I think we need intelligent algorithms. Software has a big role to play, for sure. Via intelligent architectures, I'm going to talk more about this, but we also need to do whole system designs, algorithm, architecture, device co-design, so that we can ensure that the data doesn't overwhelm our machines. There are a couple of other things. We need to take advantage of the vast amounts of data and metadata that we have in our systems. I think there's an opportunity that we're missing greatly over here. I will hopefully get to talk about that. If we actually understand what we're doing, then we can improve architectural and system level decisions. I call this the data-driven architectures. And understanding and exploiting properties of different types of data can enable us to improve the algorithms and architectures in various metrics. So these are 3 different directions, and I'll hopefully try to talk about those 3 different directions. So I think these lead to 3 different corollaries. I will deconstruct the existing architectures. Architectures today, I believe, are terrible at dealing with data because they're really designed, as I showed you, to store and move data. They're not designed to do compute. Even though we have architectures that are heavily good at computing, like GPUs, most of the GPUs is still designed to move and store data, interconnect, caches, scratch pad memory, and they're bottlenecked by the memory capacity and bandwidth. So this is because of the choice we've made. They're processor-centric as opposed to data-centric, and we're going to get to this. The second corollary is architectures today are terrible at taking advantage of the vast amounts of data that are available to them. They're designed to make very simple decisions. They're essentially designed, they ignore a lot of data when they're making decisions. Their decisions are really not data-driven. Their decisions are more human-driven. A human designer designs the architecture, and they put some policies in there, and these policies ignore the vast amounts of evidence that you can gather from the data potentially. And the third one is we're terrible at knowing and exploiting different properties of application data. I think this changes a little bit with domain-specific architectures, but we need to do a lot more, I think, in the general-purpose domain here as well. Basically, we're designing architectures to treat data essentially all the same. Even though there is vast amount of semantic information that's available at the higher levels of the stack about data, that doesn't get communicated. As a result, architectures underneath make decisions that are component aware, as opposed to the characteristics, aware of the characteristics of the data that you're fetching or doing something to. Okay, so hopefully we'll get to cover all of this before electricity goes out. But I'll spend a lot of time on the first one, and a little bit more, less time on this one, and even less time on this one. So let's start with this first one. I'll call this the first direction as data-centric or memory-centric architectures. And I think this is really a mindset. How do you redesign the entire system by making data the first-class citizen as opposed to a processor the first-class citizen? And I think there are a bunch of properties over here. I'm going to pick and choose the first 2 over here. Basically, I believe we need to process data where it resides, where it makes sense, as opposed to moving the data only into the processor before we can process it. I'm going to talk about this next, but I'm going to talk about this one first because this is also very important for a data-centric mentality. We need to enable low latency and low energy access to data. I don't think we have it today, even though we can do it today. And I think on top of this, we need low-cost data storage and processing. There are a bunch of things over here, and intelligent data management. I'm going to skip these 2, even though those are important directions. Let's start with this low latency and low energy data access. And I'll start with trends that we have in DRAM chips. If you look at the commodity DRAM chips, DDR chips, over the last 18 years until 2017, if you plot the curves of how much capacity of a DRAM chip has improved versus how much bandwidth has improved versus how much latency has improved, you will get a curve that looks nice for capacity like this. The capacity has improved a lot over the last 18 years, 128x. But you can see that we're having trouble in recent years. This is actually how DRAM manufacturers design their chips. They really focus on capacity. Okay, I'll give you the bandwidth also. bandwidth has improved by 20x. This is ignoring the mainstream technology, DDR technology. It's ignoring the HBM, HMC, or 3D stack technologies, for example. I have something to say about that later on. But if you ignore that, it's 20x. Okay, bandwidth, I think you can pay more, increase the power, and you can get more bandwidth like we've done with GDDR5. What about latency? Any guesses? How much has latency improved over the last 18 years until 2017? Flat. I can see people saying 5x. You're very optimistic. It's 30%. And if you want a product that gets you 5x today, you're not going to get it because it doesn't exist. You can get a product that gets you maybe 2x, and you have to chop off your arm and leg and give it to the DRAM manufacturers to be able to get that because it's expensive. So basically, latency lags behind for sure, and this is partly a conscious design choice. Partly it's because this is a harder problem. Capacity is easier because we can write Moore's law and also capacitor scaling. It's not easy, I'm saying. DRAM manufacturers have a very hard time scaling capacity these days, as you can see with the step function going forward, and it's going to be much worse into the future. It's going to cause a lot of reliability problems. I will briefly talk about that also. But basically, we haven't focused on latency as much, but I think latency is really one of the sources of the problems that we have with data. Because we have long latencies, we cause a lot of churn of data. And latency also affects energy, because if you have long latencies to activate a row, for example, you're wasting a lot of energy doing that activation. Okay, you can go into a little bit more detail actually. It turns out some of the latencies are increasing. There's a paper written by Samsung and Intel. I wish I had more time to put those slides over here. They say that write latencies are going to increase. We need to find solutions to it. Basically, some of the latencies are actually increasing. Yet DRAM latency is critical for performance in many of these applications. And we recently written a paper, this was presented last month at Sigmetrics, where we looked at 9 different DRAM types that are state-of-the-art, and some of them are old, some of them are new, and about 150 or so workloads. Don't quote me on the 150, it's more than 100 workloads. And we wanted to understand how these workloads interact with different DRAM types. And one of the features of newer memory technologies like DDR4 or GDDR, well, not GDDR, GDDR is actually good, DDR4 or 3D stack memories is they actually increase latency. And it turns out that a lot of workloads that are latency bound suffer from this. So one of the major conclusions that we have in the study is we should really focus on DRAM latency going forward, because a lot of workloads suffer. If you increase bandwidth, yes, you may get some workloads to benefit, but if it comes at the expense of increasing latency, you may not actually get those benefits. You may actually lose performance. We see this in this work, and I'd be happy to talk about this separately, but I'm not going to focus on this. This is hot off the press work, if you will. Okay, basically, I believe memory latency is a significant limiter of system performance and energy efficiency, and it's becoming increasingly so with higher memory contention in multi-core and heterogeneous architectures. And on top of this, if we're increasing the latencies in emerging DRAM technologies, it's not helping us. It's exacerbating the bandwidth need, but it's not clear if we increase the bandwidth, we're going to get performance, because you need to parallelize your program that way, and it may not always happen. It exacerbates the quality of service problem as well. It also increases processor design complexity, because you need to put mechanisms to tolerate the memory latency. And there are many mechanisms that we put. As a result, processors are extremely complex today. That's true for accelerators also, like GPUs. So this is a slide that I presented in my PhD proposal. If Yale were here, if he was awake, he would probably recognize this. In 2003. Basically, these are conventional latency tolerance techniques that we have used in processors for a long time. As you can see, all of these were developed in the 1960s. Of course, there are major improvements over the years: caching, prefetching, multi-threading, out-of-order execution. And all of these are actually processor-centric techniques. And if you look at all of them, they try to reduce the memory latency or hide the memory latency. But they're not really truly reducing the memory latency. They're hiding or reducing the memory latency from the processor's perspective. The memory latency is still there. You're just hiding it for the processor so that it doesn't see it. And it doesn't always work. Caching doesn't always work if you have random access patterns. Prefetching doesn't always work if you're not able to prefetch. Multi-threading always doesn't work, because you actually may not be able to do this, and out-of-order execution leads to a lot of resource consumption. So none of these actually fundamentally reduce memory latency. And we want to do that. I think it's time to actually try to fundamentally reduce memory latency. And let me give you 2 reasons why we have long memory latencies. I'll give you one example, and then we're going to jump to some other topic. Basically, there are 2 major sources of latency inefficiency today. First, modern DRAM is not designed for low latency. Main focus is cost per bit, capacity, and somewhat bandwidth. And we're seeing this mentality going forward with new memory technologies. And I think this is a very dangerous mentality. The second thing is modern DRAM latency is determined by worst case conditions and worst case devices. This is something we can do something about immediately, I believe. Much of memory latency is actually unnecessary today. And I'm going to give you an example of how to exploit this. So our goal has been for some years that my PhD thesis was actually on tolerating memory latencies on run-ahead execution, which is a basically simplified form of out-of-order execution somewhat. I'd be happy to talk about that separately. But I think I've seen the better world afterwards, thinking that maybe there's a better world if we actually truly reduce the memory latency. We don't need all these sophisticated techniques, at least to the extent we have them today. So our goal has been to reduce memory latency at the source of the problem, at memory, where the data resides. That's the data-centric property again. So then the question you ask is, why is the memory latency high? I'm going to give you one reason why memory latency is high. There are multiple reasons. One reason is memory latency that as we specify it in the DRAM data sheets. You take a data sheet, it tells you there are a bunch of latencies. It doesn't reflect the true latency of the device. Why? Because we have imperfect manufacturing process, latency variation, a lot of heterogeneity in real life. And as a result, the chips that we manufacture look like this. There's a latency spectrum that you have over here. Some chips are fast, some chips are slow. And they still operate reliably if you actually reduce the latency to this amount. But of course, within a chip you have variation also. So there are some cells that are fast, some cells that are slow. Then the key question is, can we exploit this variation? So what is done today is actually very bad. It's really the worst case determining the common case. DRAM manufacturers, or JEDEC to be more specific, they determine some standard latency that they put into the standards, and this latency is determined for reasons other than making DRAM fast, and the reason is to improve the yield as much as possible, such that the devices that you manufactured, most of them fall below this so that you can sell them. Basically, they try to maximize the yield. As a result, standard latency is very high today. Okay, so given this, what can you do? Basically, this is one of the simple ideas. We want to optimize DRAM timing parameters online. And the idea is, why don't we have 2 different sets of latencies? Of course, you can generalize the idea to n different sets of latencies, as opposed to having a single set of latencies specified for all devices operating at all temperatures, like 85 degrees Celsius. Let's also give device-specific latencies for operation at 55 degrees Celsius. Now, if you're operating at 55 degrees Celsius, all of the chart sharing process is really fast in DRAM, so you can actually fetch the data much faster. So that's the idea over here. Somebody, DRAM manufacturer, provides multiple sets of reliable timing parameters at different temperatures for each DIMM, and the system monitors the DRAM temperature and uses the appropriate DRAM timing parameters for that particular DIMM. Now, this already exists actually. You can monitor the DRAM temperature, you can get good readings. Now, somebody needs to provide this reliable DRAM timing parameters. Assume that the DRAM manufacturer does it, but we've actually developed a lot of online profiling techniques that you can do it online in the memory controller if you have an intelligent memory controller. Okay, if I don't break the electricity, maybe they will. Okay, so we actually built this infrastructure where we could test a lot of DRAM for other reasons, but we were able to test the latencies as well. So if you characterize and actually we open sourced a soft memory controller where you can test DRAM under many different conditions. So if you're interested in using this, we'd be happy to help in many ways. But we actually use this infrastructure to characterize a bunch of DIMMs, a bunch of memory modules. And we found out that at 55 degrees Celsius, you can reduce the latencies, read latencies by about 30% and write latencies by about 55% without introducing any errors. So we've done rigorous testing, and you don't get any errors, and you can do this reduction well. This is average. There's clearly a distribution across different chips because everything is heterogeneous, as I mentioned. And you can go into a lot more detail, and if you're really interested, you can take a look at the paper. We've published all of the data. Essentially, this proves that much of latency is unnecessary. If you are able to specify latency at 55 degrees Celsius, you chop off your write latencies by 55% on average. And what does this buy you in terms of performance? We've done some real system studies, and I don't think these really truly reflect the potential of the idea. But you can see that in real systems, this is real systems, we took these DIMMs that we know you could operate much faster, and we operated them much faster by changing the memory controller slightly in a real system, and we found out that you get about 14% performance improvement on these memory-intensive workloads. And you can do this in real life. You just need to figure out what latencies you can operate things at. Okay, so this also reduces energy. We showed in the paper that you can reduce power consumption because you're not activating things as long. You're not really allowing the charge to flow too much, and that actually gives you better energy. And this is the paper if you're interested. I can talk more and more about latency later. But I think I'll give you an overview of this fixed latency mindset. I call this a fixed latency mindset. Basically, reliable operational latency is actually very heterogeneous, but we're treating things to be very homogeneous with fixed latency mindset. And heterogeneity exists across temperatures, chips, parts of a chip, voltage levels, ... You can imagine many things. And our goal has been to dynamically find out and use the lowest latency one can reliably access a memory location with. And I've given you the idea of adaptive latency DRAM, but you can do this within a chip also. That gives you even more benefit. You can do this by exploiting the structural variation that you can discover about the internal organization of the chip. And then this can enable other things. You can actually look at the voltage reliability trade-offs. You can, once you actually are able to change the latencies, you'll figure out that when you reduce the latencies of some DRAM cells, they fail randomly. And you can actually generate random numbers by exploiting this phenomenon at very high throughput, at very low latency. And devices that have DRAM are can actually do this with an intelligent memory controller. So you can find out many, many interesting things, which I'm really not going to talk about, but I'm going to skip to the other direction. Basically, I think going forward, we would like to really find sources of latency heterogeneity and exploit them to minimize latency. And hopefully, along the way, enable other benefits like random number generation or physical unclonable function evaluation, some security functions that you can create. Okay, I'm going to go through some of these papers that if people are interested, they can refer to the slides. These are some of the papers that, for example, this one exploits spatial variation. Because we showed that you can do DRAM latency puffs through random number generation. And also you can exploit access patterns to reduce latency, different types of parallelism inside the DRAM. You can create heterogeneity. I didn't talk about this direction, but you can actually create heterogeneity, change the DRAM microarchitecture to actually reduce the latency at low cost. And I'd be happy to talk about that separately. This is the latest work that we present at ISCA to reduce latency, but it actually enables other benefits also. Okay, and of course getting rid of refresh is another way of reducing latency, which is very important because this is really the fundamental scaling problem of DRAM refresh and retention times. Okay, basically I'll give you two takeaways. The first one is we can reduce memory latency, but we need to change our mindset. The mindset is fixed latency. The mindset is we tolerate the latency in the processor. No, the mindset is everything is heterogeneous, so we actually figure out that heterogeneity and exploit it, and it's really about the data, not the processor. And I think we do need intelligent controllers to reduce latency and energy, because I don't think this is easy without having intelligent controllers, because there are a lot of aging issues, long-term issues that you may not be able to plan for when you actually test the latency at the beginning. So if you have an intelligent controller, you do this testing once in a while and you figure the dynamically reliable latencies over time. And I didn't talk about that, but some of the works look into that. Okay, so I spent a lot of time on latency. Now but this I think points to the data-centric mindset also. I'm going to talk about this one, which is even more about the data-centric mindset, basically processing data where it makes sense. I think these are synergistic. We want to reduce the latency as well as process the data where latency is reduced. That way we reduce the latency even more. Because there's latency that's inherent to the device. There's latency also that we have because we move the data all the way to somewhere else. So I'll start with this one. So I call this processing data where it makes sense because it's really about where it makes sense as opposed to processing in memory. Today we have no choice. We process data in the processor or the accelerators, and everywhere else is a dumb storage or data movement device. We don't have the ability to ship computation to a cache, for example, to an interconnect, for example, or to main memory or to a storage device. So this is an old idea, of course. If we had more time, I'd be happy to go through the history of it. The first paper on processing in memory was published in 1970, as far as I know, in the general purpose domain. It's Harold Stone's paper on a logic and memory computer. If somebody claims they invented it, It's really that first paper, but there may be other older papers that I don't know of. And clearly, people have looked at it over the years, and it has not realized. I believe today we're in a different situation. Today we have a huge technology problem with DRAM. There's a huge push from technology, and DRAM scaling is at jeopardy. We already have a lot of problems with DRAM, and I'm going to give you one example very quickly. As a result, people are looking at controllers close to DRAM. People are thinking about intelligent controllers. And industry is actually open to new memory architectures for a change. Basically, people are looking into 3D stacked memory plus logic architectures where you can put some logic underneath memory layers at high bandwidth, low latency connections with the memory. This is another example. And some companies are even experimenting with relatively simple processing inside the DRAM chip. And this didn't exist as much, at least in the mainstream industry, more than 10 years ago. So actually, memory scaling issues were real. This is one of the earlier papers that we wrote on the topic, which was presented in the International Memory Workshop in 2013. And they are real. Now we are writing actually papers that look like this. The Rowhammer problem, I could briefly talk about that. So basically, these scaling issues are real, and industry actually needs to fix these scaling issues. So how are they fixing these scaling issues? I think there's more intelligence to be added to the system to be able to do that. So Rowhammer, very quickly, now we can actually predictably induce bit flips in commodity DRAM chips. And this is problematic because it's a reliability problem. On top of this, it's a security problem because this simple hardware failure mechanism, the simple bit flip that happens because you're hammering a row can be exploited by malicious attackers to take over a system. And there's a lot of evidence which is actually surveyed in this paper that I mentioned briefly that I'd be happy to talk about separately. So essentially, because cells are too close to each other, we're having a lot of reliability problems. Those reliability problems are leading to a lot of bit flips, and these bit flips are predictable, and you can predictably induce them using software, and as a result, these become security problems. So it's a bit sad because technology scales down and you have the security problem. So how do you solve the security problem? I'm not going to go into a very long Rowhammer talk over here, but I believe these reliability and security problems are best solved by adding intelligence to the controller so that the controller can, for example, issue additional refreshes whenever it's needed at low cost, at low overhead. Or the controller, whenever you find out a security problem, controller has some patchability or programmability, and you can actually update the microcode in your controller such that it can do something different whenever it really potentially detects a security problem. So I think we need intelligent memory controllers because the circuits and devices are not perfect, and those intelligent memory controllers can actually make up for the fact that they're not perfect. And we already see this a lot in flash memory, for example. If you look at an SSD controller, the controllers are extremely intelligent. Well, extremely is maybe too strong, but basically they do a lot of work to overcome these reliability and security issues and keep the flash memory, which otherwise doesn't work most of the time, work, because they actually do a lot of voltage optimization, a lot of ECC, a lot of error correction, a lot of refresh, for example. So we need this in main memory as well. So we're basically pushed by circuits and devices. But we have a huge pull from systems and applications also that's pulling us to do more intelligent memory controller. Basically, data access is a major system and application bottleneck. I'm going to give you more examples. Systems are heavily energy limited today, much more so than 10 years ago. And it's going to get worse. And data movement is much more energy hungry than computation. Now let's take a look at several of these. But in my mind, I think actually, if you look at the big picture, the question I have is, do we want a world that looks like this going forward? Or do we want a world that looks like this? I think I would prefer the previous one. Previous one is more sustainable. We need energy efficiency. But I don't think we want a world that looks like this without doing anything. I think we still want to be very high performance and productive. So we want to be able to get the productivity and high performance of the second world with the energy efficiency and sustainability of the first world. And the problem is, and the computing power is growing in the world today. If we're moving data all over the system, we're going to increase the power. We're not going to be sustainable. So data access is the major performance and energy bottleneck today. But the way we're designing our systems, our design principles cause great energy waste. Basically, we're moving data all around, and they cause great performance loss because I put this in parentheses because we try very, very hard to tolerate this performance loss. We add a lot of mechanisms in our systems, prefetching, caching, out-of-order execution, multi-threading, very heavy amounts. And they lead to even more energy waste. So we're in a vicious cycle right now. To tolerate the memory latency, we actually add a lot of these complex techniques, which cause energy waste, and we're moving data to begin with to cause an energy waste, and this keeps increasing and increasing. I think we need to break that vicious cycle somehow. So I think that breaking a vicious cycle usually comes from understanding where the problem really lies. I think the problem is this: processing of data is performed far away from the data, and we have no other choice. And I'm going to go back to this picture very quickly. Basically, we've heavily optimized this computing unit over here and kept everything else dumb and essentially unusable for computation purposes. I'm going to go through this relatively quickly. Yet we very well know that the memory is the thing that's really bottlenecking us. This is actually a quote from Dick Seitz, which is a one-page paper that was published in Microprocessor Report in 1996. And I'd recommend everyone to read it. It's very instructive. After designing EV5, Dick Seitz wrote this paper saying that we designed this processor to finish 4 instructions every cycle. Yet in this important database workload, it's finishing 1 instructions every 4.5 cycles. So basically it's operating at 1/18th of its peak bandwidth. And he finishes the paper with this sentence that I finally got it right, and I was able, in past incarnations of this talk, I somehow wasn't able to get this over here. But basically he says this: I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Maybe I won't go as far as only, but this is 1996. Okay, let's fast forward a little bit. Fast forward to 2003. This is data from my own PhD thesis, run at execution. We looked at a lot of workloads Intel used to design its processors with at the time, and we found out a very similar thing basically. Most of the time the processor is doing nothing, waiting for data to come back. Okay, you don't believe Dick Seitz, you don't believe me. Since everybody believes Google, I'll give you data from Google. This is Google's ISCA 2015 paper where they said they analyzed all of their data center workloads, and they essentially say the same thing. In this really good general purpose processor, most of the time is spent for waiting for data. Only 10 to 20% of the time we can do useful work. So that's the history of about 25 years of processor design, and processors are getting faster, clearly, but they're still waiting for data. Okay, so why? Because we have a grossly imbalanced system. Processing is done in only one place, and the processor needs to wait for data to be able to do anything. And this is energy inefficient, low performance, and complex. As a result, we increase the complexity of our processors. They may also get more powerful, but this is energy inefficient, low performance, and complex. Low performance because you could actually use that real estate for something else, right? So as a result, we have this picture. Most of the system is dedicated to storing and moving data, and we cannot get away from it. So okay, let me give you the energy perspective also. If you look at the energy perspective, this is a slide that I borrowed from Bill Daly. You could argue with all of these numbers because they're technology dependent, but this is a 64-bit double precision floating point operation, 20 picojoules, expensive operation. This is a DRAM read or write, 16 nanojoules. That's 800x, and I'll give you a range over here. Basically, a memory access consumes 2 to 3 order of magnitude more energy compared to a complex addition. And I was actually in DAC recently in June, and people were talking about the AI accelerators that they design, and they were, one of the persons were actually good enough to give a real number, and they said that a memory access in our accelerator costs 160 times energy compared to a complex addition that we do. Okay, don't quote me on it. It may be an FMAC. My memory is not very good. You know, refresh problem exists in human memories too. Okay, so these are some other works that show that basically memory energy is much more costly. Essentially, and as a result, you get a picture like this. More than 60% of the system energy is spent on data movement. But we don't want to move the data. And that's how we can solve the energy problem, I think. So to be able to do this, I believe we need to have a paradigm shift to enable computation with minimal data movement. Compute where it makes sense. Have the option to compute where the data resides or while the data is moving. And make computing architectures more data-centric. I'm not sure if there is another solution to this. I believe actually there is another solution which is essentially the same principles, which is coming up with extremely fast and efficient interconnects that get rid of this dichotomy between processing, computing, and memory. Maybe you're not able to integrate computation as much as I described over here, but if you come up with a very great interconnect technology, you can also solve this data movement problem. But I think that's also proved to be relatively hard today. And at that point, I think the dichotomy between computation and memory will become invisible probably. Okay, so, but until we get to that point, maybe we should enable computation in different components that store data. And in this case, I'm giving you one example from memory. Basically, memory stores a lot of data, and we'd like to be able to query the memory, ask questions to it, and memory provides results. And there are many, many questions over here that are clear. For example, how do we actually design the memory and the controllers and the processor, the software and the hardware interfaces to enable this? We don't have either of those. How do we design the system software and the languages and the algorithms? And actually the theoretical foundations of computing assume that computation is done in some place like this. And they don't place as much importance into data. If you take a theory of computation course, how many times do you actually talk about the memory complexity or data complexity? Not as much, actually. Okay, as a result, I think we need to think across the stack, and there are a lot of things to be done for all the way from devices to algorithms. Now I'm going to give you two examples. I don't believe that putting a very general purpose, extremely high performance processor inside a memory chip is going to work. There have been proposals like that in the past. These are two fundamentally very different technologies. So we also need to think differently. I'm going to give you two examples of thinking differently. One is going to be minimally changing memory chips. Surprisingly, people have not thought about this as much. I'd love to learn more if you have actually references to this in the past, in the 1960s, for example. The second is more opportunistic. The technology has enabled these 3D stacked memory plus logic devices. How do we take advantage of them? Let me start with the first one. The first one is actually, I'm going to give you examples from DRAM, but actually many memories have this capability. Memory chips essentially have the ability to do bulk data movement and computation internally with very small changes. You can exploit internal connectivity to move data. You can exploit analog computation capability. I'm going to give you examples from DRAM quickly. But before that, we're not going to even talk about computation. We're going to talk about copy initialization, which is a primitive that's used in many, many workloads. And you build a lot of things. In operating systems, for example, you have copy on write primitives. You initialize things to 0 so that you don't leak information when you actually deallocate pages. And there are many, many use cases of data copy and initialization. And Google has shown that in their ISCA 2015 paper, more than 5% of the cycles in their data center in the same workloads that I showed you earlier, memmove and memcopy, those cycles are spent on just memmove and memcopy. And there are many, many other functions that lead to data copy that they do not even account for that over here. So how do we do bulk data copy today? If you want to copy a source page to a destination page, today we go through the processor. I'll go through this relatively quickly. Basically, you need to move the source page byte by byte all the way into the L1 or the memory controller if you set up the DMA, Direct Memory Access Engine. And then the destination page also here, do the copy and write back to the destination page. Clearly, this is high latency. You're causing a lot of churn in the system. This is high bandwidth utilization, perhaps on the most important resource that you have in terms of bandwidth. Cache pollution, but you could eliminate that by setting up the DMA engine with some overheads. And unwanted data movement, because you may be initializing a huge database without actually needing to use that anytime soon. And if you actually do a small copy, 4 kilobyte page copy via the DMA engine over here, it takes about 1,000 nanoseconds and 3.6 microjoules. Now, if you show this picture to a child, a 10-year-old child, and if you ask them the question, is there a better way to do this? I bet they will come up with an answer. And that answer may look like something like this. Why don't you do this? Basically, have set up the memory such that memory copies the source page to the destination page like this. Sometimes I think we need to think like a child, and we need to redesign our systems like children. So this is clearly low latency because you're not moving things all around, and you can exploit the internal connectivity as I will describe. You're not consuming any data bandwidth over here. No cache pollution, but you could eliminate that today anyway with DMA. And no unwanted data movement. Again, if you're initializing something huge, or if you're doing copy on write and you're not really going to use the destination for some time, you're not moving data over here. You're not wasting your precious cache resources for it. And I'll give you an example where which reduces the 1,000 nanoseconds to 90 nanoseconds. You could optimize it to be 70. And 3.6 microjoules to 0.04 microjoules in the best case. And the best case looks like this, in DRAM at least. If you find out a better case, please let me know. Basically, in DRAM, you have a subarray. Subarray rows are connected to a row buffer, sense amplifiers. And assume that we want to copy a source row to a destination row. Now, you can do this really easily. You can almost do it in real DRAM chips. Basically, you activate the source row, which brings the data into the row buffer. Now the data is strong in the row buffer. Now the next step is to activate the destination row, which deactivates the source row, activates the destination row, and the data that you captured from the source row now drives the destination row. And that's the idea. It's very simple. It's based on charge sharing principles and the fact that your sense amplifiers are extremely strong compared to your cells. This is 2 consecutive activates, negligible hardware cost, no change to the DRAM interface really. You just need to be able to 2 consecutive activates. Of course, you want to generalize it. You can generalize it with some more hardware cost, but not a lot actually, because there's a lot of internal connectivity. You can move data between banks, between subarrays. I'm not going to talk about that. In the best case, you can reduce the 4 kilobyte page copy latency by 10x, and memory energy that you consume in 4 kilobyte page copy by 74x. And I think this also leads to a different way of writing software potentially, because all of the companies that write software that do a lot of copying today, they get rid of that copying by making their software extremely complex. They jump through a lot of hoops to be able to do that. VMware is one example, because they had to do a lot of copying when they manage virtual machines. And if you actually have copies that are really fast, maybe there's a different way of designing software actually. Okay. So basically, the thinking is memory is another accelerator. And what does an accelerator mean? You design something that's good at some specific things. And there are some functions that memory is very good at, copying and initializing. Initializing is a special case of copy, is one example. Maybe we need to start thinking that way. We're designing all these accelerators over here. They're all sitting on the left side or the wrong side of the memory bus. But there's an accelerator to be built over here that's sitting on the right side of the memory bus, which is not bottlenecked by this memory bus as a result. And I think you can argue, of course, programming is hard, but we've been programming these accelerators also. So you basically need to build the infrastructure to be able to program these things. Okay, similarly, we can support more things. Basically, we can support and or not majority bitwise. I'm going to give you the example very quickly at low cost by exploiting the analog computation capability in DRAM. Again, the same principle. Chart sharing works very well. It's analog computation. And DRAM is very nice because not everything stays analog. The sense amplifier converts things to digital. So the idea is very simple. You activate multiple rows to perform computation. And this leads to significant performance and energy improvement in these block bitwise operations. I'm going to give you an example. I'm going to give you a story about this paper also. But later, actually, people have looked at emerging memory technologies to do similar things. And I believe there's even more potential with new memory technologies like memristors, phase change memory, STT-MRAM, ... whatever you have, because fundamentally, DRAM is destructive. Whenever you do a read, you fundamentally have to move the data somewhere, slightly. Even if slightly, that costs energy and performance. But in these new memory technologies, you don't have to move the data because they're non-volatile. You can operate on data in place, assuming you actually fit your algorithm to the form of the memory technology. Basically, I think this is very important to pursue. I'm not going to talk about new memory technology, but there's a lot of work going on in this, and I believe you need to encourage even more work in this direction. So let me give you in DRAM how can you do AND and OR bitwise. Basically, imagine that these are 3 rows. They're 8 kilobyte wide, let's say, but I'm going to show you a single bit line over here, ABC. And you can imagine that this is in a single subarray, but you have thousands of subarrays if you build your DRAM nicely. And assume that we have the primitive to concurrently activate these 3 rows. I call this a triple row activation. If you do this, all of them get connected to the bit line at the same time, and assuming an ideal circuit, what happens is if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. Now what does that mean? That's essentially logically a majority function. Basically you have a bitwise majority that you can do in a single cell and across cells independently. And this is beautiful on its own. Majority function, I think, has a lot of beautiful properties. Knuth has realized them in his chapter 4. And there's actually work that has been done at EPFL, for example, to map a lot of logic design completely into majority functions. It's beautiful. But you can do more. Basically, you can rewrite this simple Boolean equation by taking out C. If C is 1, you get the OR of A and B. If C is 0, you get the AND of A and B. Now you can do bitwise AND and bitwise OR by controlling what you have in C over here. Now that's beautiful. But of course, it's beautiful, but maybe not enough. It's not functionally complete. You need a NOT to be able to make it functionally complete, and as a result, a general purpose computation engine. So essentially that's what we did. NOT is a bit harder, unfortunately. It exists, actually. The complement of a bit that you read exists in the DRAM chip. It exists in the other side of the sense amplifier, except it's not connected. This is really not connected back into the array. So basically the idea is to connect it back into the array to a special row. This adds a little bit more overhead, and we've done a lot of work in this paper over here to examine the implications of it. But now you can get a NOT also. Essentially you have a bulk bitwise computation engine in DRAM, and as long as you can write your algorithm to be able to fit the form, then you can actually take advantage of this bulk bitwise execution engine. And the benefits are essentially a lot. Not energy, performance improves a lot, energy improves 60x, let's say over here, and then you can do AND and OR, you can do NAND and OR, you can do XOR, XNOR. Of course, you can build these primitives, and the paper shows some ways of building these primitives. Later, other people showed that you could do it on emerging memory technologies. Other people also showed building on our work that you can improve what we've done. Basically, you can do much better than this. These numbers are from our work. You can actually do better than this. Okay, so if you don't want to fit the form to fit the function to the form in this case, it turns out there are some functions that already fit to the form, almost. Basically, if you're doing a lot of bulk bitwise operations, there are some cases where you're doing a lot of bulk bitwise operations, like bitmap indices that are used in some databases. Jignesh Patel's group in Wisconsin, they designed this database called bit weaving. They actually wanted to maximize the bitwise operations that they do. Well, we have only 5 minutes, really? Okay, I thought we had 55 minutes more. Okay, I'll try to speed up. Basically,
the lights is gonna go.
Otherwise, the lights are gone. Okay. Basically, the bit weaving database is designed for GPUs that can do bulk bitwise operations really well, but it's a very good fit. There are web search engines, DNA sequence mapping, encryption algorithms, set operations. There are many, many things. And if you actually do this, it's an old slide, unfortunately. Basically, you get 5 to 6x performance improvement in the query latencies. And if you actually take this database and put it on the substrate we have, you get 4 to 12x performance improvement on that substrate. So there are a lot of benefits to be gained over here. Okay, so that's the paper. Sounds good, no? Okay, if you actually write a paper like this is mainly for the younger folks over here, you get reviews that look like this. Very clever, novel idea, great potential to speed up an energy gain. Sounds great, right? Well, the weaknesses. Nobody will build this. Okay, and reject. This paper did not appear in ISCA. Another weakness, basically the same thing. Another weakness says, this is a circuit paper, you have no business publishing in computer architecture. Okay, so basically I think we have a reviewer accountability problem that we need to fix. I have to point this out also. Apparently I captured this over here. So we thank all the reviewers that have reviewed this paper over the conferences for sure. I think this is not a way to fix the problem for sure, but I think it's a way of acknowledging the problem to begin with. But if you get reviews like this, don't get discouraged. I think there's, believe in the idea, follow your passion. I'm very passionate about, for sure, this particular example. And it turns out, very interestingly, we put an archive report on this, and some people, before we published the paper itself, archive report, some people already built on our work, and they showed that you could do these bulk bitwise operations on phase change memory, and they published it before us. But they were nice enough to actually acknowledge our archive report, saying that they got the inspiration from our work. So I think the reviewers actually have a big accountability, and they may be delaying progress in the world. Okay, so don't get discouraged, basically. We need to work on enabling the better future for sure. We do need to fix the reviewer accountability problem, and just like memory needs intelligent controllers, we need accountable reviewers. Okay, so let me skip this part, because you tell me we have really 5 minutes? No, we still have time.
Much less now.
Much less now. I'm not sure. It says 11:23. Okay. Let me quickly go over this. Basically, we have 3D stacked memory, and there are many things you can do in 3D stacked memory. One of the things is you can build an accelerator for graph processing. Graph processing is a very good example for putting stuff in memory, because you have a lot of random memory access and you have relatively little amount of computation. And when you have something like this, you don't want to be moving the data all the way into the processor, because all of your caching hierarchy is designed for exploiting locality, and you don't have a lot of locality. So basically we designed the system that's called Tesseract. It's essentially a parallel computer that consists of memory plus logic chips. And if you look at inside this chip, you have these vaults that have memory controllers inside, and we basically put simple in-order cores in them. And you program these in-order cores using message passing. You lay out your graph nodes on top of these vaults, and whenever you want to actually operate on a graph node, you send a message to the processor that contains the node. Basically, we get rid of cache coherence. It's all physically addressed, no virtual memory. So the hard problems with hard problems with moving data to moving computation to data actually get solved over here or ignored. But this works well like a GPU, initial form of a GPU, because now you actually operate on graph nodes wherever they reside. Of course, you need to partition your graph somewhat nicely, because if you really want to have a large graph, you actually have many of these chips together, interconnected in some way, and we have a programming model that takes advantage of it. It's essentially essentially a distributed system-based programming model that's done on an accelerator that looks like this. Again, I don't have a lot of time. You can read the paper for more detail. We have some prefetching mechanisms. I'll give you the results very quickly. Basically, the system looks like this. It's not similar to existing systems because it doesn't have the processor-memory dichotomy, as you can see, but you expose a lot of bandwidth to the aggregate cores. It's about 8 terabytes per second in that times technology. So what are the benefits you get? Averaged across 5 graph processing algorithms, we get significant performance improvement and significant energy reduction also. I believe this can be optimized. Actually, there are a lot of works that are built on this work that show that you can get even more significant improvements. One of the reasons is they use very large data sets, so they see a lot higher numbers like 60x, 70x. They also do better graph partitioning, better optimization of the system. As a result, they get much better performance. Okay. So let me go through this relatively quickly also. I think we still have some time.
No, we don't.
Okay, we don't. I'm going to skip this one, but basically you can do this by simple function offloading on mobile devices, and you can get significant performance energy improvements with that also. Let me switch to this other thing over here. Basically, we need to enable somehow processing in memory, but I think there's a lot to be done over here. There are a bunch of barriers to adoption. I think the key is really by changing the mindset, we can fix the problems. So we really need to revisit the entire stack to be able to enable something like this. And if you're really interested, we have a paper that reviews some of the open problems in the area. So we need to enable computing architecture with minimal data movement. There are 2 other topics, but let me quickly go over this one because this is really important, and I think this is something that people have not been doing as much. We are designing these AI accelerators, but we're not thinking about using AI or ML as much to improve the systems that we design today. I call this exploiting data to design intelligent architectures. If you look at system architecture design today, it's very human-driven. Humans design the policies. As a result, you have many too simple, short-sighted policies all over the system. And there's no automatic data-driven policy learning. There's almost no learning. We don't actually take advantage of the past actions that we've done. Clearly, there are branch predictors, for example. They try to optimize things based on the past, but they're not really learning. Well, perceptron predictors are a difference, actually. They're a single-layer network that are being used right now. So the key question is, can we design fundamentally intelligent architectures? And I think a fundamentally intelligent architecture is much more data-driven. It makes decisions based on data. Machine learns the best policies and how to do things. You have sophisticated, workload-driven, changing, far-sighted policies. And this requires automatic data-driven policy learning, and all controllers are intelligent data-driven agents. So the question is, how do we get there? I think this is not an easy problem. Basically, we need to rethink the entire designs that we have, and also we need to change the mindset to enable that rethinking. I'll give you one example of the work that we've done 11 years ago, very quickly. Basically, we realized that memory controllers are hard to design. If you look at a memory controller, it actually does a lot of things. It obeys DRAM timing constraint, it keeps track of many resources, it needs to handle refresh, manage power, optimize performance, and quality of service. Actually, this, in my opinion, this is really the center of the world in an SoC like this. And also, it needs to, it's one of the hardest parts to design. And you can see there are a bunch of timing constraints, and there are reasons for it. I think this is a good example of where we may want to have homogeneity. There's a lot of heterogeneity in the design. But actually, the design is becoming more difficult. This part is becoming more heterogeneous. This part is becoming more heterogeneous, and you're squeezed in the middle, again, as a memory controller. So how do we actually design the memory controller? So our dream, the reality at that time is that it's difficult to design a policy that actually gives you good results. There are too many things to think about for a human designer. And you have continuously changing workload and system behavior. How do you design a policy that can adapt? And as a result, human designers don't design policies that adapt. They basically look at the current state, and they basically take a decision, and done. Of course, it doesn't work well in many cases. So wouldn't it be nice if a DRAM controller automatically found a good scheduling policy of its own? So I'll give you the key idea over here. Basically, we realized that a memory controller that can adapt its scheduling policy using machine learning can do much better. And we realized a particular machine learning algorithm, reinforcement learning in this case, maps nicely to memory controller because you actually have a lot of data going through the memory controller that you can learn from. So a memory controller is essentially a reinforcement learning agent. It dynamically and continuously learns and employs the best policies to optimize long-term performance. So if you look at reinforcement learning, classically, you have an agent that observes a state, takes an action to maximize a long-term reward. It gets a reward based on its action. It basically changes the weights so that it can do a better action, hopefully, in the same state when it sees it again. So a memory controller essentially works this way. There's a lot of theory associated with it. Memory controller is a Markov decision process, actually, which you can prove a lot of things about this. And I'm not going to go through the detail, but basically the paper has a lot of details over here. You need to figure out your reward functions, you need to figure out your state attributes you examine, and you need to figure out the actions that you need to take. The hard part is actually this. Now the human designer needs to do this. The human designer doesn't need to come up with a policy. They need to come up with all of this, which I believe is easier. Of course, it still needs to be done, and the complexity shifts to actually figuring out all of these. So it's a different design mindset, actually. And if you actually do that, it turns out you can get large, robust performance improvements over many human design policies. And this is, I believe, the beginning of it. There are works right now. Clearly, I believe the only example where learning is employed in modern hardware chips is the perceptron predictor, which is the branch predictor. But it's a very simple form of learning, but it's made its way inside. And there are works that are looking at prefetching, for example, going into the future. But I believe we need to actually rethink the entire architecture, because there are a lot of benefits. You get continuous learning, reduced design burden. Of course, there are some downsides that we need to somehow solve. Okay, if you're interested, this is the paper, and I'd be happy to talk about it. So basically, we need to rethink the design of all controllers, and to make computing architectures more data-driven or more self-optimizing. So I'm going to skip this one, data-aware architectures. I think this is really important, but basically, we don't have time. Georgi says I don't have time, so we don't have time. But this picture basically tells it all. You have all the semantic information, and you're wasting all of that information by going through this ISA funnel today. So why don't we make this funnel much bigger such that we can express things much better? And if you actually do that, you get a lot of performance again. And we actually did some work with NVIDIA to express locality better. And this is already being implemented in the future NVIDIA chips. Another example is hybrid memory. If you actually have an expressive interface, you can specify the properties of your data. Let's say tolerant and vulnerable. Today we don't do that. And you can design a memory system that's much better. I'll just animate these so that you can get the ideas. Okay, so basically if you know the properties of your data, if you're more expressive, you can design a much better computing architecture, I think, because we're wasting a lot of semantic information at the top. Okay, so let me conclude. I believe it's time to design principled system architectures to solve the data handling or memory and storage problem. We have a huge data handling problem and we need to solve it. But to be able to solve it, we need to really go back to the basics, the first principles. We want to be balanced. We're violating that balanced design principle from the very beginning today. Why? Because we can process data only in one place. And as a result, we have 10% of the time, 10% of the resources dedicated to processing data, 90% of the resources waiting idle, and wasting a lot of energy going through. So basically, we want to be truly balanced, high performance, energy efficient. I think this is what I mean by an intelligent architecture. And these follow: data-centric, data-driven, data-aware. I believe this can lead to orders of magnitude improvements. I've given you some examples of this. Enable new applications and computing paradigms. I think we're really bottlenecked by this. This is not enabling new applications. The nanopore sequencing has a lot of potential. We're wasting a lot of that potential. This could also enable better understanding of the nature, because if you ask psychologists in the 20th century, they were fascinated by computing as a way of understanding humans. Well, that effort failed miserably, because computers don't work the way humans actually think or behave. Maybe if we actually make computers more like the nature, we can have a shot at understanding the nature better. And maybe you can enable other benefits over here. So basically, we need to find the principles of computing a bit better, but we need to think across the entire stack and get there step by step. Okay, do I want to go through this? I think I will go through this very quickly, but basically these are the principles. And I will point out this one over here, so that maybe Soner asks a question. I think this is a fundamental principle that we cannot really forego in any way, because actually it's very tightly coupled with better than worst case design. So if you actually have a worst case, if you're homogeneous, you'll have to account for the worst case. But if you're heterogeneous, you don't care about the worst case. Worst case takes as long as it takes. Well, you may care about the worst case for other reasons, but you don't design the entire system to be the worst case. But for all of this, I think we need open minds. And I think I'm on time. Yes, Georg.
So, you prove that time is relative.
Absolutely. But we knew that before.
Because this is actually part of the remark. It is not the memory, but is physics. So people forget, Onur, that moving data at 1 millimeter costs time. And this is the main source of latency. And in this universe, we cannot do anything to cope with that. So I was hoping, by the way, when the colleagues in Delft published this thing, the Bell paradox experiment, that they can communicate between two entangled particles with zero latency. I said, now we can build interconnect that has the zero latency that we need.
That'd be nice.
They had to disappoint me. I'll talk to you about that later. But so it is indeed the basic laws of physics, like the speed of light, that drive that interface. And we have to build the memory controller, I agree with you, in a way to appreciate that latency. Not mitigate it, not hide it, but appreciate it and do some useful work for that time. Understand it and do that. You give the example of the flash controllers as being more intelligent, which is the case, however, it is driven by a completely different objective.
Yeah, absolutely.
Doing the wear leveling mitigation, again, because there is a finite number of times you can flip the bear gate. But again, this has to do with basic physics. And the question is how we can force computing system in that corner that by necessity designers will start making the memory controllers more intelligent.
So the reason I gave the flash controller is basically for scaling issues. If you look at the way it handles reliability issues like wear leveling or many other voltage optimization, flash memory, if you look at the bits that come off, they don't work. Memory controller is the thing that makes it work. So I agree with you that it's not more intelligent than that. They don't do other stuff. So how do you change the designers to do more? I think people will have to do it more going forward, for sure.
They will not. Because they're lazy. The thing is how we can create this content is not that they are forced to do that.
So how do you force them to do that?
Exactly.
That's a good thing we can brainstorm about. Yes?
I actually have two comments. One is the fact that this is already going on if you look at the really high level. I mean, if you have a terabyte, petabyte data set, everybody knows that they have to ship their computations to whatever data center in the world that thing is going on. Amazon has this wonderful pile of satellite photos, and the only way you can get to them is like move your compute to the data center, because otherwise you'll be spending a year, moving the whole damn thing through the internet, right? And the other one is this: there's an interesting kind of backlash against things like NAND memory controllers, because right now there's a very strong movement just remove that stupid controller out of the loop because it adds latency, it adds stuff you don't want. I mean, if you're a user and you know what you're doing, you can actually get direct access down to the NAND chip. So now it's all up to you. Do the wear leveling, do the placement in your application level. And that's another way to do this, right? If you just expose enough stuff to the software for the truly critical stuff, it actually might make sense to go to the utter pain of dealing with the hardware, from the application level, which is completely contrary to what we typically do when we hide that, inside operating system and try and be like, oh, let's hide all this nasty stuff. So I think there's a trend towards exposing all the nasty stuff to software as well, which probably goes hand in hand with this.
Yeah, I agree that it goes hand in hand with what I mentioned, exposing. I mean, if this were a longer talk, I would talk about breaking those interfaces so they can expose more to the software. I agree that people are trying to ship computational data. That's why I meant the distributed system-based programming model, right? People are actually trying to ship computational data at the higher level, but it's really not happening in the fundamentals of how we build a device. And that's wasting a lot of energy to begin with. Basically, I think we need to take that mentality inside the device itself as well.
Now it's time for the next session, so I need to next questions for offline. So thank you again.
Okay, thank you.